Hello, grade 12s. Today we are going to be looking at lesson 2, which is on Euler's number, and lesson 3, which is exponential equations. So I have a TI-84, which I think most of you have, so you'll be able to follow along whenever we use the calculator. So let's get started with a warm-up. Without graphing or using your calculator, describe the graphs of the following functions. So for A, it says that y equals 3 times 2 over 5 to the power of x. So remember that all exponential equations can be written in the form y equals a times b to the x. So that means that we could write this in this form, although it's already written in this, but we could automatically realize that the 3 here is in the a position, the 2 over 5 is in the b position, and then x is x. So the great thing about this is that if it's in this, we automatically can tell a couple things, whether it's increasing or decreasing, and also the y-intercept. So the a value is equal to the y-intercept, so that for this first graph, our y-intercept is going to be 3. That's where it crosses the y-axis. So if we have a graph like this, this is my y-axis, so that means it's going to cross at approximately 3. And then whether it's increasing or decreasing, we can tell that by b. If it's 2 over 5, it's less than 1. So 2 over 5, you can think of that either as a fraction or as a number. If you take that and divide it on your calculator, 2 over 5 is equal to 0.4. And 0.4 is less than 1. If it's less than 1, then we know that it's decreasing. If it's greater than 1, that means it's increasing. So let's look at the second one here. We have y equals 4 to the power of x. This one could be tricky because it's not exactly in our exponential form yet. Y equals a times b to the power of x. We just have y equals 4 to the x. So if you can look at that, you will see that there's no a. We have b, which is 4, but there's no a. So we can rewrite that as y equals 1 times 4 to the x. And the reason that we can put a 1 there is because it doesn't change the value. So our y-intercept is now much easier to read. We know that y is a, so that means our y-intercept is going to be 1. And b tells us whether it's increasing or decreasing. In this case, 4 is greater than 1, so it is increasing, going up. All right, let's look at question number 2. Which exponential function matches each graph below? Provide your reasoning. Scroll down. Okay. So we have y equals 3 times 0.2 to the power of x, y equals 4 times 3 to the power of x, y equals 4 times 0.5 to the power of x, and y equals 2 times 4 to the power of x. So the great thing about this question is that all of them are already in exponential form, a times b to the power of x. So right away, we should be able to tell whether it's increasing, whether it's decreasing, and the y-intercept. So first off, let's look at the y-intercept. For this one, it's 3. For number 2, it's 4. For number 3, it's 4. And for number 4, it's 2. So let's look at our graphs. Here we have a y-intercept of 2. So the only one that has a y-intercept of 2 is 4. So right away, we're done 1. Perfect. Now let's try C. C has a y-intercept. It looks like it's going to cross at 3. Right here. Sorry, a little bit of that. So we can tell that the only one that has a y-intercept of 3 is 1. So this one's going to be I. All right, so now this one we're in a bit of a predicament. We see that both B and D have y-intercepts of 4, but we can tell that one of them is increasing and one of them is decreasing. So which one's increasing and which one's decreasing? If we look at 2, we see this one has a b value of 3, and if we look at 4, we can see that, or sorry, 3, we can see that this one has a b value of 0.5. So 0.5 is going to be decreasing. So that's this one. It goes from top to bottom. It's D, and then B is going to be the other one, 2. And there you have it. You can match it without even using your calculator. All right, last warm-up question. Write an equation to represent the functions described below. Y-intercept is 4 and it's increasing. So remember y equals a times b to the power of x. And now we can just plug in numbers that satisfy these two things. So the first one is that the y-intercept is 4. So that means that a equals 4. And then it says it's increasing. If it's increasing, you can use any number as long as it's bigger than 1. So I'm going to use 2 and then to the power of x, and that's it. Okay, the second one, we have y-intercept is 7 and it's decreasing. So once again, start with y. It has an intercept of 7, so 7 goes in the a spot, and then it's decreasing. So this time I'm going to use 0.5, but really you can use any number less than 1 to the power of x. All right, let's move on to our new material here. Today we're learning about Euler's number. So I'm not sure if you have heard of E before, but that stands for a constant called Euler's number. It's an irrational number just like pi, except for this one is 2.71828. And we actually have this button on our calculator. I'm not sure if you've noticed it before. Okay, so E, let's turn this thing on, is right here. Second function, ln, and that gives you E. So if you go E to the power of 1, which remember raising anything to the power of 1 is just itself, you should get Euler's constant, which is 2.718281828. So it's in no particular pattern because it's irrational. So this number occurs naturally in some situations where a quantity increases continuously, such as an increasing population. So let's try using this. It can be used for exponential functions fairly easily. So predict the number of x-intercepts, the y-intercept, and the end behavior, and the domain and range of the following function. Y equals e to the x. So remembering that our form is y equals a times b to the power of x, we can see right again that there's no a. So let's place that in. We can have y equals 1 times e to the x, and that's not changing anything. So we now know that our y-intercept is equal to 1 because a equals 1. Number of x-intercepts. This doesn't change for any exponential function. There's always no x-intercepts. So you can either put none or 0 because it doesn't cross the x-intercept. And behavior. This also doesn't change from any type of function. So we're going to put 2 to 1. And now let's go ahead and try graphing this. So click on your y-enters, y equals. And now we are going to second function ln, and we get e to the power of x. Go ahead and graph it. Your window settings should be in your standard. So your domain and range, just like any other exponential function, is going to be the same. We have x can be any real number, and y is greater than 0. All right, so we can see that this is a type of exponential growth that we can use in populations. So if you're ever asked to use an equation that involves e, we'll also be using it in logarithms. Except for in logarithms, we actually use this ln button here. Okay, so we have our graph. We can see that it still takes on the characteristics of any exponential function. It's just we know that 1 is going to be our y-intercept because we can rewrite it in the form. All right, let's switch to our lesson number 2. All right, lesson number 3 is up, solving exponential equations. The reason we're doing 2 lessons today is that first lesson on Euler's numbers really quick. So let's move on to lesson number 3. We're now going to move on to solving exponential equations. We're going to go through a few different types. The first type is where x is the base. So you notice in our example, there's an x for the base of all of these examples. And we're going to use reciprocal power to both sides. When you put the power into your calculator, the power must be in brackets. So we'll go through that on the calculator. So let's try solving the first one here. X to the power of 3 equals 32. So it's pretty clear that this is not what we would call a perfect triplet or a perfect cube, because there's no 3 numbers that we can multiply together to give us 32. So for example, 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. So there's not going to be any easy whole number that gives us 32, which means that we have to be able to solve this. So we're going to solve it using the reciprocal power to both sides. So what that means is using an inverse function. So the opposite of raising something to the power of 3 is actually raising something to the power of 1/3. So if I have x to the power of 3, first off we need to go over what a reciprocal is. So if I have 3, and I'm writing on this side here, the reciprocal of that is switching top and bottom. But this number doesn't have a bottom. So we can add a bottom on this one. Remember, any number, if we divide it by 1, is still equal to itself. So then its reciprocal is switching the top and bottom. So it's going to be 1/3. Okay, so we have x to the power of 3. If we want to raise it to the power of its reciprocal, we're going to raise it to the power of 1/3. Why would we do this? Well, x to the power of 3 to the power of 1/3, if you remember your exponent laws from grade 10 or grade 9, that if you're raising a power to a power, we can multiply those exponents. So it becomes 3 times 1/3. So we can put this over 1. We now get 3 times 1 is 3. 1 times 3 is 3. 3/3 is 1. X to the power of 1 is itself, so therefore we can solve for itself. But remember, if you do something to one side, you have to do it to the other side as well. So this side becomes 32 to the power of 1/3. So these cancel out and just become x. And on the other side, we have 32 to the power of 1/3. We can type that into our calculator. Oopsies. I don't know how to get rid of this. Here we go. All right, so 32 to the power of, our little tippy hat thing, 1/3. So this calculator is a newer version, but for most of you guys, you will have to put the 1/3 in brackets. Otherwise, it'll raise it to the power of 1, which is 32, and then divide by 3, which is not what we want. So make sure you put the top in brackets. And then we get our answer, 3.17. We'll round it up to the nearest tenth for 3.2. So that means that 3.2 to the power of 3 equals 32, approximately. All right, let's move on to B. Similar idea here. We have x to the power of 4th equals 20. So we take x to the power of 4. If we want to solve for x, we raise it to the power of the reciprocal. 1/4 equals 20. If we did it to one side, we have to do it to the other side. And remember, the reason we can do that is because 4 times 1/4 is 1. So we get x to the power of 1, which is just x. Right, now we use our calculator. 20 to the power of bracket 1/4 equals 2.11. So once again, nearest tenth, x equals 2.1. All right, moving right along. So remember, we got those numbers by taking the reciprocal. So for this one, when it says x to the power of 2 over 3 equals 64, we're going to do the exact same thing. We have x to the power of 2 over 3, and we're going to raise it to the power of the reciprocal. Reciprocal of 2 over 3 is 3 over 2, flipping top and bottom, equals 64. And then if we do it to the other one side, we do it to the other. So once again, the reason we can do that is because 2 over 3 times 3 over 2, try it on your calculator if you want to, is equal to 1. So let's raise 64 to the power of 3 over 2 equals 512. So x equals 512. And of course, you can always go back and check your answer, which I will do on my calculator by raising 512 to the power of 2 over 3 and make sure that we get 64. If we got 64, boom, we did it right. All right, last example, we have x to the power of negative 3 over 4 equals 125. So we have to raise it to the power of its reciprocal. Keep in mind that reciprocal is just changing top and bottom. It doesn't, however, change the sign. So that means I multiply it by negative 4 over 3. And it doesn't really matter where you put that negative sign. If you wanted to keep it with the 3, that would be fine. Equals 125 to the power of negative 4 over 3. So those cancel out, the negative 3 over 4 and the positive 3 over 4. And let's type that in our calculator, 125 to the power of negative 4 over 5 equals 0.210. So sometimes these numbers are actually just disguised fractions. So always check once you're finished if it can be written as a fraction. You'll do that by pressing the math button, 1 for fraction, or enter, and enter. Okay, this one was not a fraction. Okay. Oh, I wrote down the wrong number. Lovely. Okay, so this one should have been 4 over 3. So let's try that again on my calculator. 125 to the power of negative 4 over 3 this time. Oh, much better. 0.0016. Now we can turn this into a fraction. And it gives us 1 over 625. So x is equal to 1 over 625. All right, I'm going to give you a couple minutes. You can pause the video to fill in these charts. You can do them all on your calculator if you want, or maybe you'll start to see a pattern and you can do them without a calculator. All right, so here are the answers. Make sure you check them. These powers are very important. Some of them will become very second nature to you, so you'll have to memorize some of them in order to make type 2 equations much easier, especially the power of 2's and some of the lower power of 3's and 4's. All right, so let's move on and see if we can solve type 2 equations. All right, so we have some steps here. Notice that x is no longer the base, and that's what type 1 equations were. Now let's solve type 2. X is the exponent. So write as a common base, make an equation using only the exponents, and solve. So let's solve the following equations. What do these steps actually mean? So what it means is that we can rewrite some of these numbers using the same base. So 2 is already a prime number. We know that there's no way that we're going to be able to simplify that. So let's draw our attention to the 8. The 8 can be rewritten as a power of 2. If you look on your chart from the page before, it says that 2 to the power of 3 equals 8. So what we do is we rewrite the equation, leaving everything else the same, except for changing the 8 to 2 to the power of 3. because 2 to the power of 3 is the same thing as 8. And then now that we have the same common bases, we make an equation using only the exponents. So you might want to think back to rational expressions where we dropped the bottom. Now we get to drop the base of the exponent. So we're going to be left with x minus 1 equals 3. So we only take out, I'll show you what we take out if I can here. Highlighter. So we only take out the exponents. But we can only do that once the bases are the same. Just like in rational expressions, we can only do that once the bottoms are the same. And now we have this beautiful, easy type 1 equation to solve, where we have x minus 1 equals 3. We add 1 to both sides, and we get x equals 4. Now, it's a really good habit to get in to start checking your work. This one you can do pretty easily in your head. You could put the 4 in for the x and get 4 minus 1 equals 3, 2 to the power of 3 equals 8, which we know to be true. Awesome. First one is finished. Let's try that for the second one. How can I rewrite one of these numbers so that they have the same base? 3 is a prime number. We know that we're not going to be able to multiply 3 anything or make it lower, so that means the 27 is going to have to be used. So hopefully by now you know that 3 to the power of 3 equals 27. So 3 to the power of 2x minus 1, we rewrite the same, but we change 27 as 3 to the power of 3. Now if you need to, make a list of your common squares and cubes on the side of your page. It'll make your life a lot easier. Now that the bases are the same, once again we can drop them and we get 2x minus 1 equals 3. Now we have a simple two-step equation to solve. Remember, we do the opposite of order of operations, which means we add or subtract first. In this case, we're going to add 1 to both sides. It cancels off here. We get 2x equals 4. Divide both sides by 2. X equals 2. So the solving equations, that should be the easy step. We're mainly learning that you have to get the base the same now. All right, good. Let's move on to the next slide. You can see we're getting a little more complicated here. So now we might have to change two numbers. So in this case, we can rewrite 9 as 3 to the power of 2. 3 to the power of 2 means 3 times 3, which is 9. But then we still have that 2x minus 3 there. So we are going to leave that in brackets like that. 2x minus 3. And we need to write 27 with a common base of 3 as well. So on the previous page, that 3 to the power of 3 is equal to 27. So now we just put 4x plus 2 in brackets here. All right, now that we have the bases the same, we can drop them. We have 2 times 2x minus 3 equals 3 times 4x plus 2. So I noticed that on your exam, we were having a little bit of trouble distributing. We tend to multiply the first one by, but we forgot to multiply 2 times the negative 3 as well. So please don't forget that. So 2 times 2x is 4x. 2 times negative 3 is negative 6. Have to do the same thing on this side. We get 12x plus 6. 3 times 4x, 3 times 2. All right, now we have a bit more complicated of a equation to solve. First step is to get our variables together. So let's subtract 4x from both sides. 4x minus 4x is 0. Those cancel out. We get negative 6 equals 12 minus 4, which is 8x, plus 6. Now we have to move our constants. So we have minus 6. Cancels out, minus 6 here. We get negative 12 equals 8x. And I'm guessing you guys have less room than I do. Now we divide both sides by 8. And we get x equals negative 12 over 8, which can be simplified to x equals negative 3 over 2. Good, that's our answer. So it's not always going to be super nice numbers, although that one's not too bad. All right, second one, or D. We have to write them with the same base. So try to think of a couple numbers that we could break down into, and remember your perfect squares, 2 to the power of 2, those kind of numbers are going to come in really important here. We can rewrite 8 as 2 to the power of 3. And then remember the 2x minus 1 stays after that. We can rewrite 16. 16, 2 to the power of 4. And then 2x plus 3. All right, now that we have the same bases, we can drop everything else. We have 3 times 2x minus 1 equals 4 times 2x plus 3. Remember to expand. 3 times 2x is 6x. 3 times negative 1 is negative 3. 4 times 2x is 8x. 4 times 3 is 12. Collect your like terms on one side. I'll subtract 6x from both sides. Those cancel out, and I'm left with negative 3 equals 2x plus 12. Move the 12 to the other side by subtracting it. I get negative 15 equals 2x. And I divide both sides by 2. And I get x equals, oops, negative 15 over 2 is my answer. All right, let's skip E and move to F. I'm also going to teach you a bit of a hint how you can check your answers. However, you need to make sure that you know how to do it algebraically, because you will be asked on quizzes, tests, and your diploma to be able to do it algebraically. This is just to check your answers. So sometimes if you can't find a common number, so example 6, there's no way that we can rewrite 27 as a power base of 6. So is what we do is we take the left-hand side and put it as y1 in our calculator, and take the right-hand side and put it as y2. So we go to our calculator. Oh. Okay, we go to our y editor, clear what you have. You're going to put 6 to the power of x in for y1. Move down to y2, put in 27. Now we press graph. All right, there's 6 to the power of x. And y2 equals 27, you're not going to be able to see, which means let's try zooming out. Sometimes you'll have to play around a little bit with it until you're able to find it. Another thing that you'll be able to get better at is knowing what window settings you'll do. Okay, so there we can see our first line went straight up, but our 27 is finally on our screen. So is what you can do now to find the answer is find the intercept. So in order to do that, you press second function, calc, get this nice list. We've used 0 before. We might have used intersect. We're going to find the intersect. So press 5. It can be a little tricky to tell which curve it's on. However, right now I think that it is on that first curve, 6 to the power of x, so press enter. Second curve, good, it jumped to that line already, so just enter, enter, enter again, and it'll tell us the answer. So it tells us that x equals 1.83. How nice. So x equals 1.8. So let's round to the nearest tenth. And you can check that if you want by taking 6 to the power of 1.8 on your calculator, and you should get something close to 27. Remember, it won't be exact because we're rounding. All right, let's try the next couple. Same thing. y1 is equal to 2 to the power of x minus 3. So this one put in as y1, this one here as y2, and then you find the intersect. So just so you know, when you're doing a quiz or a test, you have to tell me what you did. So you can't just write down x equals. You need to tell me that you put this one in as y2, this one in as y1, and found the intersect. So let's go to a y editor, clear what we have. y1 is 2 to the power of x minus 3. Same thing here. We need to make sure that our exponents are in brackets. y1, let's put in as 5. So notice here I interchanged them. That does not matter at all. You just need to know which one it is to pay attention to where they come up on the screen. I'm going to try zooming it back to standard. We'll see if we can see. So the y equals 5 is there. And there's a 2 to the power of x minus 3. Perfect. So now we press second function calc, find the intercept. So 5. Here's line 5 and 2 to the power of x minus 3. Enter, enter. And there, it spits out the answer for us. X equals 5.32. Round to the nearest tenth, 5.3. All right, last one. Put this equal to y1, this equal to y2, and intersect them. Find the intersect. So I just want to reiterate, you're doing this because you cannot find a common base. 5 and 7 are both prime numbers. There's no way that we can rewrite those with the same base. So sometimes you'll be able to rewrite them with the same base, sometimes you won't. If not, this is your method. All right, here's my y editor. Let's clear it. Okay, y1 is 5 to the power of bracket 2 minus x, don't forget your brackets, and 7 to the power of 3 plus x. All right, let's graph, see if they come up. All right, there's our first one, and second one. So you cannot see where they cross, so let's try zooming out. Oh, maybe you can see where they cross. Let's see one more time. So I have a feeling let's try. Sometimes you can't actually see where they intercept, so let's just try graph or calc, sorry, intersect, enter, enter, enter. And in this case, you can't actually see where it intercepts, but it's at x equals negative 0.7. So you won't always be able to see. So always just try it, and then if not, you can zoom out. 0.7, rounded to the nearest tenth. Awesome, time to do some practice. Let me know if you have any questions tomorrow. I will be back.